Hello everyone, this is your little summary of complex numbers. So first of all, I is the square root of -1. This is the first time we're able to take square roots of negative numbers. The powers of I form an I sequence. So we know I squared is going to be -1, and therefore I to the power of 4 is going to be 1 because I squared will give you I to the power of 4, okay? And I squared multiplied by I will give you -I. But after that, once you hit 1 and you multiply that by another I to get I to the power of 5, we're back to I. So I, see the pattern here? I squared, I cubed, I to the power of 4 is exactly the same as I to the power of 5, 6, 7, 8. So the pattern continues, and you'll notice that I to the power of a multiple of 4 will always be 1. That could be helpful to know. You need to know, so every complex number can be written in the form x plus yi, where x is the real part and y is the imaginary part. And actually in a question, if it says, if it gives you a z and says, write z in the form x plus yi, immediately write z in that form, because there's more information to be had by seeing it with its real and imaginary parts than just looking at z. The conjugate of a complex number, z bar, is x minus yi, so you just swap the sign there of the imaginary part. The modulus is the square root of x squared plus y squared. Note, I doesn't appear anywhere in the modulus formula. It is just the square root of x squared plus y squared. We need the quantity under the square root to be positive, okay? And also note, so if you took z and multiplied it by z conjugate, x plus yi by x minus yi, you end up with x squared plus y squared, which is the modulus of z to be squared. Just a little note there. And also the modulus of z is the r in polar form, because you know your r in polar form is this quantity here. So there's a few little things there that tie it together very nicely. Conjugate roots theorem. So if 2 plus 7i, here it is by example, is a root of this quadratic, where a, b, and c are real numbers. This is key. The conjugate roots theorem only works if the coefficients here and the constant are real. So if 2 plus 7i is a root, then 2 minus 7i is also a root. Only works if the coefficients are real. But if the coefficients are real, then you have conjugate roots, which means if you have a complex number as a root, then its conjugate is also a root. When you're solving complex equations, so when you have like a quadratic equation, we try to get everything to one side and 0 to the other. We have a plan when we recognize a quadratic equation. For a complex equation, I would keep complex numbers on both sides, because when you tidy everything up, you can put real equal to real and imaginary equal to imaginary. And that gives you extra information. It looks like you've only one equation and suddenly you have two equations, because you have a real equation, you have the imaginary equation. So just keep complex numbers on both sides of the equation and equate real with real and imaginary with imaginary. We do that a good bit in complex numbers. Quadratics and roots. And this is true for any quadratic. If you have a quadratic with 1 as the coefficient of x squared or z squared, then the number in front of z, the coefficient, is minus the sum of the roots, and the constant at the end is the product of the roots. So there are 3 things to remember here about the coefficients. If the coefficient of z squared is 1, then you know the coefficient of z and you know the constant. That can be very helpful in constructing quadratic equations or picking them apart. To get to polar form, z equals x plus yi to go to r cos theta plus I sin theta. If you're in doubt about actually what polar form is, if you forget that formula there, on page 20 of your log tables you have De Moivre's theorem, and in the middle of De Moivre's theorem they express a complex number in that form. So to get to polar form, you can use a button on your calculator, but you also need to know how all these x and y's and r's and thetas relate to each other. So we already had that r is the square root of x squared plus y squared, which is the modulus of z. We know that the tan of theta is y over x. So you find the tan inverse of y over x to get the angle theta. But plot z, because if you, there's half a chance that theta will be right and the half a chance it'll be wrong, because there are 2 quadrants where tan is positive and 2 quadrants where tan is negative, okay? So always make sure to plot z as well. So just in terms of polar form, what you're getting there is the modulus r is the distance away from the origin. So this here is the modulus of z, which is equal to r. This is x plus yi. And then the angle theta, known as the argument, is the angle that that line makes with the positive x-axis, the usual way we measure our angles. And then, so if z, plot z, and you may need to adjust theta because, perhaps you got theta equal to 45, but then your actual complex number is down here. Then you would have to take 120 and add 45, and that's not a very 45 looking like angle, but you know what I mean. For general polar form, which sometimes we will need, and I'll tell you when in a moment, or cos theta plus add your extra rotations, 360 degree n, or in radians 2 pi n. And here's an example. So z is this, or is square root of 8. Tan inverse of -1 is -45. So -45, the angle is down here, okay? But when you plot the complex number, -2 minus 2i, it's up here, okay? So we have -45. In fact, if you add 180 in the case of tan, it'll bring you to the correct angle. But also you recognize that this is 45, and therefore the angle we want is 135. So the complex number in general polar form is √8 cos 135 plus 360 degrees n. And then that second angle always matches, or should always match. Okay, a few more things. When you're multiplying complex numbers in polar form, you multiply the r values and you add the angle values, r by r, add the angles. When you're dividing complex numbers in polar form, you divide the r's and you subtract the angles. The angle from on top is you take from it the angle from the bottom. And then De Moivre's theorem is on page 20 of your log tables. Okay, so if you're raising z to a power, it is r to the n, and you multiply the angle by n. This might help you remember the multiplication of complex numbers above, because if you're raising r to the n, in that instance, what you're actually doing is, what you're doing is you're multiplying r by itself n times. Okay. And then, complex numbers in the arc-n diagram. There's z, 2z is along the same line out of the origin, but the distance is twice the distance from z to the origin being 0, 0 here. And then minus z is in the opposite quadrant. Z bar is going to be down here. Z bar, the conjugate, you keep the same x component and you change the sign of the y component. Iz is z rotated anti-clockwise by an angle of 90 degrees. Because when you multiply by I, the complex number I is in its polar form, so its distance away from the origin is 1, there's I. Or is 1, so it's 1 times the cos of 90 degrees plus I sine 90 degrees. So when you take any complex number and you multiply it, and we know when we multiply it, we multiply the r's and we add the angles. So 1 isn't going to affect the r, so this new iz is still the same distance away from the origin as z. We add 90 degrees to the angle, that's why we end up rotating it anti-clockwise by 90 degrees. Express cos theta in terms of cos theta. It's a tricky little proof. So what you do is you want to relate cos 3 theta to cos of theta. We can do this one actually in class later. Just let me know if you'd like to. So first thing you do is you use De Moivre's theorem to relate cos theta plus I sine theta to cos 3 theta. So that's what De Moivre's theorem would give us if we raise that to the power of 3. Then you can expand the left-hand side using the binomial expansion. And then you put real equal to real and use this fact. So they're the bare bones. There is a description in the footer notes actually in complex numbers, but we can also go through it later if you'd like. And then finally, powers and De Moivre's theorem. If you're asked to write this to the power of 6 in this form, you have to go through polar form, use De Moivre's theorem. Like you could multiply it by itself 6 times, but obviously that's not what you want to do, you know. So get 1 minus √3i to polar form, use De Moivre's theorem, and just notice that this question, asking you to write 1 minus √3i to the power of 6, could be asked in a different way. You could be asked to solve this. And to solve that, you'd need to raise both sides to the power of 6, so z is 1 minus √3i to the power of 6, and then you go ahead and do exactly as above. And then if you have a fraction in the power, so if you would need to write 1 minus √3i to the power of a third in the form x plus yi, you need to get your complex number to general polar form. Use De Moivre's theorem as above, And then in general polar form, you'll have plus 360 degrees n or plus 2 pi n. You start letting n be 0, 1 and 2 until the solutions begin to repeat themselves. And similarly, this could have been asked in the following way. Solve z cubed. So to solve z cubed, you'd say z is 1 minus root 3i to the power of a third, and you go ahead as above. And this is the thing with kind of slightly unusual complex numbers like 3i. To get that to polar form could be a little tricky. Its distance away from the origin is 3. The angle it makes with the positive x-axis is 90. Look at minus 4. Its distance away from the origin is 4. The angle it makes with the positive x-axis is 180. And then 2, its distance away from the origin is 2, and the angle it makes with the positive x-axis is 0. Now, if you have any questions about any of that, let me know either during the day, send me a message, or send me a message at the beginning of Zoom, and I'll talk through any of the points there that didn't make any sense. Okay, see you later.